taking questions from section 2.1, if anybody's done anything from there that have to ask questions about. So last time we talked about section 2.1. I had assigned that you guys could do up through 24. None of that's due this weekend. It's due next weekend. So if you didn't start, no big deal. But if anybody has and want to talk about anything, I am open for business. What do you guys think? Anybody interested? Yeah, Jacob?
You said the homework's due next weekend, right?
The 1 through 24 is due next weekend. That's what we're talking about right now. Okay, very good. If you guys change your mind, we can always talk about it again next week. Not a big deal. That being said, let's pick up where we left off in chapter 2 then. Sound good? All right. So again, what we're going to be doing in chapter 2 is going to be generalizing our definitions for sine, cosine, tangent from our geometric definition that was locked inside of right triangles and extending those definitions outward so we can handle sine, cosine, tangent of any size angle. Before we continue with that process, let's just rehash kind of where we left off. So in geometry, we said, okay, if I have a right triangle with acute angle theta, relative to theta, this side is called the adjacent, and then the green side is called opposite, and the blue side is called hypotenuse. Well done. And we used the acronym SOHCAHTOA to help us remember the definitions for sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, and tangent being opposite over adjacent. Now, at any point, have you ever looked at those ratios and wondered, like, why did we decide on sine being opposite over hypotenuse? Couldn't we have just, like, why not do hypotenuse over opposite, or like one of these? I mean, there's other ratios I could have written from that triangle. Why do we settle on these three for sine, cosine, and tangent? Why not the other three possibilities? Well, we didn't just pick these three. We actually did all of 6 of them. So there are 3 others. So the first one we'll talk about is called cosecant, which is hypotenuse over opposite. Yuck. There is secant, which is hypotenuse over adjacent. And then there's cotangent, which is adjacent over opposite. Oh, what am I doing? Saying stuff without writing it, huh? That's too messy. And at this point, you're like, Mr. Kulik, more stuff to memorize? I don't want to have to deal with this. I just learned SOHCAHTOA. Well, hold on, because it's not really so much to memorize. We're not really going to memorize 6 more ratios. Do you notice the relationship between sine and cosecant? They're reciprocals, right? And cosine and secant, also reciprocals, and tangent and cotangent. Okay, so rather than memorizing 3 new ratios, all I really need to memorize is which one is the reciprocal of sine, cosine, and tangent. Now, I'm going to assume that it's going to be easy to remember that tangent and cotangent are reciprocals, right? Because they both have tangent in their name. So all I need to do is remember then that sine goes with cosecant and cosine goes with secant, right? So no cos go together. Cosine does not go with cosecant. The cos don't go together. And then that means that cosine would have to go with secant, and then by process of elimination, cosecant goes with sine. And now I've managed to memorize 6 new ratios with really only remembering one thing, is that cosine and cosecant don't go together. The cos don't cooperate. Ha 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 ha. So that should feel much less overwhelming than like tacking on 3 more ratios or whatever. All right, let's do a quickie example. So let's say we want to find the exact value for the 6 trig ratios given this situation. All right. Well, wait a tick, Mr. Kulik. I can't write down a bunch of those ratios because I'm missing one of the sides of the triangle. Oh no, what should I do? Pythagorean theorem. Great. What's the Pythagorean theorem again? A squared plus b squared equals c squared. What do I have to be careful about when using this? The hypotenuse has to go into C. Does it matter which one A and B is? No. So we just got to make sure that we're finding the correct, or putting the hypotenuse into the correct part of the formula, right? Everybody happy with what we did there? NBD, right? Why didn't I round that and create a decimal? The directions ask for an exact value. Very, very good. Good at paying attention. Bless you. All right. So sine theta is going to be anybody? Yeah, 5 over the square root of 29. Now, what do you guys think? Does that look okay to you? No, what's wrong with it?
Oh, this one's like...
Yeah, we have square root in the denominator. Well, I can fix that pretty easily. So I'll just multiply by the conjugate to rationalize the denominator there and have 5 root 29 over 29. From here on out, can I just say that that's what I'm doing and not show the work for you guys? If I'm going to do something like that, we're all okay with rationalizing a denominator. I can just say what I did and then write the rationalized form. Okay. I just want to we're communicating, right? I don't want to start doing something if you're like, wait, hold it. I'm just checking. All right, let's do cosine next. What's that going to be? Great. So it's adjacent over hypotenuse, so 2 root 29 over 29. And when you give me the rationalized denominator, 2 root 29 over 29. I'll usually write at least that second step in the notes where we're not just go straight to the rationalized form. Because if you go back and look at it, that may not be super clear as to where that came from. Yes, Thomas. Of course. Of course, if you do that on the test or whatever, that's fine. Right? You can just go straight to the rationalized answer. There's no work to show here. Tan theta is 5 over 2. Okay. Let's do the rest of this. Cosecant theta should be, yeah. Mr. Kulik, how did that person do that without being able to look at the triangle? Well, they just remembered that cosecant's the reciprocal of sine. So we just looked at our answer from sine and wrote down the reciprocal. Notice that I looked at my first answer and not the final answer. Why didn't I want to look at the final answer? When I made the reciprocal, I'd have to then rationalize the denominator again and like reduce fractions. It becomes like a whole thing. Like, that's part of the reason why I wrote down that first step. Because I knew I was going to do this, so it just saves me the hassle of having to explain it later. It's almost like you've done this already today. I have. And what's the value for secant then? Square root 29 over 2, right? And the value for cotangent? 2 over 5. Hey, Macy. Just running late?
Yeah, like a full day late. I just got here.
Oh, okay, fair enough. Everybody happy with what we did there? Real easy, right? NBD? All right. Let's say so let's say that we have some angle theta that's an acute angle on a right triangle. And we know that the sine of theta is 1/3. And we want to find the exact value of the other 5 ratios. First step I would do is, draw a picture, right? We were talking about a right triangle. So start by doing that. Great. And then what is the sine of theta equaling 1/3 going to tell me? Great, the opposite side is 1, the hypotenuse is 3. How am I going to find that third side? Pythagorean theorem. Tell me what to write. Awesome. Everybody's cool with where those numbers came in? So B is going to be the square root of 8. Can I do better than that? Yeah, remember how to reduce radicals? What I'm going to think of is I'm going to ask myself, are there any perfect squares that are factors of 8? Sure. 4 times 2 is 8. And the square root of 4 is just 2. So we could write that as 2 root 2 would be the preferable way to write that. Everybody remember doing that last year in Algebra 2? Or earlier, perhaps, if you had a real good algebra or geometry teacher, you probably did that in those places also. Okay. All right, so we already have sine. So we need cosine. We need tangent. Let's do cosine, and then we need the other three, but I don't have space. So let's do cosine first before I start going crazy. What do I write here? 2 root 2 over 3. Wonderful. Tangent, what do I write there? 1 over 2 root 2. Do I like how that looks? No, what's wrong with it? Square root in the denominator. How am I going to get it out? We can just multiply the top and bottom by root 2 over root 2. You don't need to use the 2 also. It's not wrong if you do that, but you'll be left with some reducing. So when I multiply root 2 times root 2, I get root 4. And the square root of 4 is just 2. So I end up with root 2 over 4. I showed a lot of work there. You don't need to show all that work on your paper, but they're notes. That's an easy mistake to kind of forget that root 2 times root 2 gives you regular 2. If I just write it that way, figured on the first one will at least show some work. I'll get lazy about the work in the future, which you're free to be lazy about the work on little simple computation like this. Provided you're confident you can do things, correctly with skipping all the steps or whatever. But all right, then we have cosecant theta, secant theta, and cotangent theta. What's cosecant? 3 over 1, the reciprocal of sine. I'm just going to write it as 3. You guys are cool with that, right? Secant is going to be 3 over 2 root 2, which will rationalize to that. Notice I skipped some steps there and just did it. Everybody's okay? Refer to the tangent one if you're confused. And what's the cotangent going to be? 2 square root 2 over 1, or just 2 square root 2. Is everybody real happy with what we've done so far? Pretty easy, NBD. Easier than the last section probably even, right? Yeah. Sometimes that's how it goes. Okay. What if I asked you to do ask you to find the value of sine of 30 degrees without using your calculator? Without my calculator, Mr. Kulik, what do you suppose I'm going to start by doing? Drawing a picture. Okay, so here's my right triangle. There's a 30-degree angle. What now? Great, so the other angle needs to be 60. Wait a minute. That's one of the special right triangles. That's the 30, 60, 90 triangle. I remember the ratios of side lengths for a 30, 60, 90 triangle from geometry because I was a really good student. I memorized it back then. The short side is length x. The medium side is x root 3. And the long side is 2x. Again, the easy way to remember that, the way I like to remember it, is I know that the shortest side is opposite the shortest angle. The medium side is opposite the medium angle, and the biggest side is opposite the biggest angle. Remember that the square root of 3 is just a decimal. It's somewhere between 1 and 2. I think it's like 179 or something. The other way sometimes people remember this is just that the 3's are next to each other. The 30 degree and the root 3. Is that something you should remember? Yup. All right, so once I have this right triangle drawn out, though, with the sides labeled, sine of 30 is just going to be opposite over hypotenuse, or just 1/2. Oh, cool. What's the other special right triangle? Yeah, that's the 45, 45, 90. This one is usually easier to remember because the ratios, the legs are x and the hypotenuse is x root 3. These will be quite useful in the near future. Those are ones that you'd probably want to hang on to and remember. Okay. What if I ask you to find sine of 17 degrees? Yeah, notice the directions there are not specific. You should use your calculator. Before I do this, though, what do I need to check on my calculator? I need to check the mode, right? Because this is a 17-degree angle. So to do that, I'm going to press the mode button right next here to the blue second command. Make sure that the degree option is highlighted. If it's not, I just move my cursor down and press enter to highlight the degrees. Once I'm done with that, I press second in mode to exit back out. And then I can just type in sine 17 into my calculator as I would normally. And I get about 0.29. Oops. That was color coding. Everybody cool with that? What if I wanted to do secant of 78? Oh, well, Mr. Kulik, it's the same thing. I'll just go fire up my calculator and type in secant of 70. I have, yeah, I don't have a secant button on my calculator, but I can do 1 over the cosine of 78 on my calculator. So a couple of different ways you could do that. You could use the fraction command and do 1 over cosine 78. That's okay to do. You can just do 1 divided by cosine 78. That'll give you the same thing. Or you could do cosine 78, make sure you've closed the parenthesis and then do the reciprocal button. That'll give you the same thing. What you have to be careful about is that you don't do something like this, where you forget to close the parenthesis and you do the cosine of 1 over 78. That's not the same thing as 1 over the cosine of 78, right? Everybody catch that? So lots of different ways you can type in your calculator. Any of those ways is fine. It doesn't really matter. They all give you the same thing. Everybody feel good about doing that? Okay. Helpful to go see it on the calculator and like what you can do or not do? Probably. I don't know. If you have calculator questions, those are always things I'm happy to answer. All right. Last example in this section, and we're going to move on to the next one. Yes, sir. I do not. Do you want to run to the bathroom to do some nose blowing? It's allergy season. My wife's been sniffling all morning. I was like, "Are you getting sick or you just have allergies?" She's like, "I don't know. Probably allergies." She's been sick for like a month. She's been miserable. It's not fun. Anyways, this problem says solve the triangle. What's that mean when we have the direction solve the triangle? Find all the angles and sides. Great. What do you want to do first? The angle on the inside, I think? What's that angle got to be? Yeah, so let's call that x. You say it's 49. How'd you get 49? That's correct, by the way. Okay, x equals 180 minus 90 minus 41. That'll do. You could have also just done 90 minus 41 in a right triangle. That's like the corollary to the triangle sum theorem, I think is what they call that in your geometry textbook. How sad is it that Mr. Kulik like remembers the names of the geometry theorems from your textbook when he hasn't taught the course in like 10 years? Yeah, in your faces. All right, what do you want to do next? Leg or hypotenuse? Leg, okay. To do that, what am I going to use? Tangent, I agree. Relative to the angle in question, we know the adjacent, and we're looking for the opposite. So I am going to be using tangent. To solve for y, I multiply both sides by by 12, and then I just type it into my calculator. And I get about 1043. And then I guess the last one we'll call, oh, I've been meaning to color code these. Oh, well. Last one I guess we'll call Z. How do you want to solve for this? Okay, you could do that. Is there a more accurate way to do it than that?
Yes, decide.
I could use cosine, right? Why is cosine going to be more accurate than doing the Pythagorean theorem? Not that that was the wrong answer. I want to be clear. What's going to be better about this calculation than doing?
More exact.
Yeah, I have a rounded answer in here that I'm using. I have no rounding going on in here. I'll get a slightly better answer. Now, for the purposes of like you guys taking a test, it does not matter. But if you're working for NASA and trying to land a spaceship on the moon or something, you know, like a couple of decimal points of accuracy make a big, big difference. You know, it's good enough. I missed the moon. Oh well. That's $1 billion down the tubes on that rocket because we forgot to use the more accurate answer. So it doesn't, I mean, I want to be clear, like it does not really matter, but for what we're doing, because none of us are landing on the moon tomorrow.
I don't know about that.
Oh, okay. You got some SpaceX $1 million tickets to go to the moon? Actually, I don't even think they're taking you to the moon. I think they're just taking you out of the atmosphere. Far enough that it's legally called space, and then coming back. You get like 30 seconds of weightlessness or something, and then you're back down. It's $1 million later. Or whatever they were charging. You guys hear about that? I think William Shatner paid to go, which makes sense. Captain Kirk from Star Trek. That's part of the joke. Apparently he's worth like a fortune though, because instead of taking like a fee to do the like that hotel commercial, like the hotel website commercial, he took stock options. Apparently made like hundreds of millions of dollars off of that deal instead of just taking a salary. So, yeah, it's a good story. Probably made more on that deal than his entire acting career, which is pretty funny. Anyways, you guys feel good about this? This should have been largely geometry reviews, not a big deal. If it was a big deal, make sure that you kind of refresh on these kind of basic geometry skills. As they're foundational, but we can't spend a ton of time here on this. The point of doing this now is pointing out to you that when we did sine, cosine, and tangent, we're stuck operating only on angles between 0 and 90 degrees. Yes, sir.
Sorry, is Z 15.4 or 15.9?
That's a 9.
All right.
Yeah. There we go. It's the curse of bad penmanship, or being 8th hour anyways. I feel like at the beginning of the day, my penmanship is decent. By the end of the day, it just turns into other garbage. So feel free to ask. I know it's not great. So we're stuck dealing with angles between 0 and 90 degrees, right? And even if in the land of geometry, what's the biggest angle we draw in geometry? 180, right? What's a 180 degree angle look like? Straight line. Because in geometry, when we drew something like this, if we're talking about the angle measure, we're always talking about this angle, right? Why, is there any reason why we couldn't describe this angle? Just kind of convention, right? Well, that is kind of the case. So notice when I'm drawing this, like my arrow starts at this side. We'll call this the initial side of our angle. When I draw this little angle or this arrow rotating around, where we started is called the initial side. And we'll name the other arm of our angle, the one where the arrow stops at, the terminal side. That's convenient naming since it describes exactly what's going on. Initial where we start, terminal where we stop. Everybody's okay with that? And here's the clever idea. What we can do is we can take any angle and we can embed that angle into the XY axis, where we can draw the terminal side, or I'm sorry, the initial side on the positive x-axis. The vertex of our angle will always be at the origin. And then we can imagine our terminal side starting at the initial side and rotating to give us a new angle, right? Everybody's cool with that? This setup is called a standard position angle. So when we write an angle in standard position, we take the initial side, lock it onto the positive x-axis, the vertex at the origin, and then we take the other arm and we rotate it about the pivot point at the origin. So notice here that when I drew this rotating green arc, I drew it counterclockwise, right? Was there any reason I couldn't have drawn this rotating arc clockwise? No, right? We could do both. And since we can do both, we're going to use both directions. So when I do the counterclockwise rotation, we're going to call those angles positive. And when we do the clockwise rotation, we're going to use those for negative angles. Is everybody okay with what we've done here? So now, looking at what we've done so far, we've extended the angles that we can draw geometrically from 0 to 180. That was the old geometric size of angles we could draw, right? From 0 to 180. Using this, we can now draw angles from negative 360 to positive 360. Everybody okay with that? But we're not done. It's like we're on an infomercial, right? But wait, there's more. What we're talking about is just a rotation, correct? So skateboarders and snowboarders in the room, if we talk about like a 540, what's that? It's like 1.5 spins, right? So if I were to take an angle of 540 degrees, I would go 1 full rotation and then half a rotation more. So that's like a 540, right? Oh, Mr. Kulik, so I can just keep spinning around in circles and we'll still call that an angle that we can draw? Yeah, we will. So what have we just done by adding in this rotational piece? What size angles can we draw now?
Infinite.
All real numbers, right? Any size angle you want, we can draw it. 1,452 degree angle? Yeah, it's going to be a lot of spins, but we can do it. Is everybody okay with what we've just done here? Paul? Sure. Now, hopefully, when you look at this, you notice that if I drew a 180 degree angle on the same axis, the initial side and terminal side are identical. They're in the exact same locations, right? You guys see that? If we eliminated the rotational piece, the little drawing that I made, we have the exact same picture. Well, those kind of angles are going to get a special name. We're going to call these guys coterminal angles. So these are angles with different measurements. But have the same, actually let's say have identical terminal sides. This idea will become quite useful in the future. So let's take a moment and just kind of do some examples here. So let's say we want to find two angles coterminal to 47 degrees. All right, well, bless you. I guess, Mr. Kulik, I'll start with a picture. 47 is what that number says there. So I don't know, that looks like about 47. I'm not going to put the angle measure on there. Everybody agree with that? Okay, so something coterminal to that, well, I can just do one full rotation and then 47 degrees more. Everybody agree with that? Does that feel okay? And, well, if I want another one, what can I do? Instead of doing one full rotation to start, I could do
Two.
2. So 1, 2. So 1 rotation, 2 rotations, and then 47 degrees more. Gets me to 767. Now take a look at these 3 numbers. Do you notice a pattern here between these 3 numbers? What am I adding? 360. Yeah, we just add 360. Keep adding 360. Oh, Mr. Kulik, that's it? I just take the number, and if I keep adding or subtracting 360, I'm going to keep getting coterminal angles? Yeah, man. Did you even have to draw this picture to start with? No. But, like, I needed to do it to, we're building intuition right now. We're doing notes. We're not just like, how can I show you to do the problem as quickly as possible? Right? Jacob. Certainly. You guys almost have been slamming the water at lunch today, guys. Woo! Stay hydrated. All right. What if instead we want 2 angles coterminal to pi over 3 radians? Oh no, Mr. Kulik.
Oh, that would be too
Okay, so why 2 pi? Yeah. Remember that in section 2.1, we encountered the conversion factor that 180 degrees was equal to 2, or was equal to pi radians. So clearly then, if I multiply both sides by 2, 360 degrees is the same as 2 pi radians. Everybody agree with that? So I can just take pi over 3 and add 2 pi to that. To add those 2 things together, what do I need? Common denominator? Yeah, that's exactly right. That common denominator would be 3. So I end up with pi plus 6 pi all over 3, or 7 pi over 3. Yeah, because we're always, just like it's always adding 360. Yeah, absolutely. Okay. And so let's just do it again. I'm just going to write this as 6 pi over 3. Is that okay? Everybody's cool that why the 6 pi over 3? It's the same as 2 pi. I just wrote it with a common denominator. So this is my first coterminal angle. This is my second. I just took my answer and added 2 pi again. Is all I did. I just wrote my 2 pi as 6 pi over 3. And then I'm done. Now notice both of these times I elected to add. Would have been okay to subtract? Yeah. Could have you done 1 add and 1 subtract? Yeah, but you would have wanted to start with the original angle when you did the subtraction for the second angle. If you subtracted from your answer, you just gotten the first one over again. We don't want that. So just as an aside, if I have some angle, how many angles are going to be coterminal to it? Infinitely many, right? Everybody cool with that? You just keep going and spinning. You can go as many spins around as you want. Every angle has infinitely many coterminal angles. Okay, cool. All right. So I get it, Mr. Kulik. We got these, now with my angles, I can draw an angle of any size I want. Negative infinity, positive infinity. Any size you give me, I can draw that angle. It just needs to be this standard position angle that's embedded in the XY axis. Cool. I can do that. So what does that allow me to do? Oh, this is where things start getting good. Come on in. Howdy, how are you? I do. She's in the very back. Rotation. Yeah, it's a bad looking O, huh? If you had the RO, that probably would have got you there. Because the O looked like a 5 or something, it was a problem. Okay, so in the previous section, we talked about these standard position angles. Is everybody okay with what I've drawn here? This is basically what we've done, right? Now, with the terminal side, I can pick any point on that terminal side because it's just a line. It's infinitely many points. Let's just say I pick some point P on that line. That point is going to have coordinates x, y. Everybody cool with that? What I can do then is I can build something called a reference triangle. I'm just going to redraw that down here so it's not so messy because the picture gets a little crowded here. What is the length of this leg on my reference triangle? X. Very good. Why is it X? Well, it's not full 45, 45, 90 triangle. Yeah, it's because how did I get to P? I went X over, and then I went Y up. So this side then must be Y. Everybody's okay with that? So this side here, I'm going to call R. What is R going to equal? Just the square root of x squared plus y squared. What is that really? Just the Pythagorean theorem, right? Can we see that? Is everybody okay there? So if I wanted to talk about my values for sine, cosine, and tangent, and equivalently my other three trig ratios, cosecant, secant, and cotangent, sine is, using the reference triangle, opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. cosecant is the reciprocal of sine, so r over y. Secant is the reciprocal of cosine, so r over x. Cotangent is the reciprocal of tangent, so x over y. Again, we should probably, assuming that x doesn't equal 0 and y doesn't equal 0. Sorry about that. Well, I don't have to worry about r equaling 0. Well, it's a length, right? It's the distance from that point to the origin. Right? This is r. R is not a coordinate. It's a distance from the point to the origin. That distance is never going to be 0. You're not going to pick the origin as your point on the terminal side. That's not allowed. But any other point on the terminal side is. And certainly the terminal side could lie on the x or y axis, so x or y could be 0. But what have we just done here? What did we just do? We have translated the definition of sine, cosine, tangent from using the side lengths in an acute right triangle to using the point on the terminal side of our standard position angle. Everybody's okay with that? And why is this a big deal? What kind of angles can we draw as a standard position angle? Any size angle we want. What we have now unlocked is a way to find sine, cosine, and tangent, cosecant, secant, cotangent, on an angle of any size. Positive infinity or negative infinity. We can go all the way in between. We now have a way to do all of them. What? This is great, Mr. Kulik. This is great. Let's do an example. We've just shattered the mold here, guys. And you're like, it just looked like you did SOHCAHTOA, Mr. Kulik. Let's demonstrate. All right. The point, negative 3, 4, lies on the terminal side of a standard position angle, theta. Find all 6 trig ratios, and we're going to do that in the exact values for those. All right. Yeah, SP is standard position. I'm going to draw a picture to kind of illustrate what's going on, just to reinforce vocab and conceptually what's going on. In practice, you would not need the picture to do this. Is everybody okay here? So if I build my reference triangle here, this is what I build. Everybody's okay with that? So I'm just kind of reinforcing with what I did before. There's no reason that I would actually need to construct that drawing to do this problem. But I'm just going to kind of draw it in there so you can see what we did visually, because I think that helps build out your intuition and understand conceptually what's happening. Okay, so what I have a value for x, I have a value for y, and I have a value for r. All I'm going to do is fill in my formulas now. So sine is y over r. Done. Cosine is x over r. Done. Tangent is y over x. Done. Cosecant is r over y. Done. Secant is r over x. Oops. Done. Cotangent is x over y. Done. Whoa, Mr. Kulik. That is A-okay, pretty darn okay with me. Right? No big deal? Okay. What if I'm not given the point? What? Let's say we want to do cosine of 150. All right, well, let's do that then. So I'm going to draw my 150-degree angle. Yeah, Talika. Of course, yeah. So I'll start by drawing my initial side. And then what quadrant is the 150-degree angle going to lie in? Second quadrant, right? It's going to be over here somewhere, right? Do I care exactly where it is, Mr. Kulik? Not really. It's going to be in the middle-ish of the quadrant, you know, but it needs to be, you need to put in the correct quadrant. Everybody's cool? So this is 150. And I'm going to pick, you know, this will be my point P. Everybody's cool? Okay. I'm going to build my reference triangle now. Everybody's okay? And somehow I'm going to use this reference triangle to figure out the values for x and y. The key is, what does this angle have to be? 30 degrees. Excellent. Why is it 30 degrees?
180 minus 150.
Great. It's a linear pair with the 150. Everybody see that? If that's 30, this angle has to be, and what are we in? The 30, 60, 90 special right triangle. Yes. So if I do that, instead of like X when I wrote the 30, 60, 90 triangle here, when we did it back here, I'm going to use a different letter instead of S or X because I don't want to get confused with the X coordinate in the picture that we've drawn. So I'm going to use the letter S, I think. Does that sound okay to everybody?
Sure. Yeah.
I just want to, I'm trying not to double use variables. It's a little like really abusing notation there to have the sides like, oh, I'm talking about the X coordinate and then a variable named X also. That seems like, Mr. Kulik, that's pretty crappy of you. No, that's an S, not a 5. Yeah. I didn't want to use X because that was the X coordinate, so I picked a different variable. Should I use A?
Five.
I'll use A. Well, again, if you're going to go back and look at this, somebody already was like, is that a 5 or an S? That's a valid comment. Let's just make it an A. All right. But really, A is like just a placeholder, right?
Yeah.
Does it matter what A is equal to?
Yeah.
Not really. Because here's why. Here's why it doesn't matter. Does it matter where P is on the terminal side?
No.
No. Any point on the terminal side would be okay. As a result, that value of A, the ratios are going to be the same whether I picked A equal to 1, 2, 3, 4, 16.8. You can pick A to be whatever value you want it to be. Guess what I'm going to pick it to be? You guys are crazy. Now let's just do 1. So this becomes 1, that becomes root 3, that becomes 2. So what do I have here? X is equal to square root of 3. Y is equal to 1. And then R is equal to 2. No, I solved it, right? This is the X side. This is the Y side. And this is the R side.
But for A, you just put 1.
Yeah, I mean, it just, if you don't pick 1, you'll just have more reducing to do when you build your ratios out. I mean, you can pick whatever you want, but it just means like makes your life harder later on. You know, if you do 2 when you do the reduce, when you build your ratios, you'll have to reduce them all, which is fine, but like, why bother? You know? Okay. So if I do sine theta, y over r. Cosine theta, x over r. Tangent theta, y over x. But we should rationalize that. Cosecant theta is r over x, or just the reciprocal. Secant theta is equal to 2 root 3 over 3, and cotangent theta is equal to root 3 over 1, or just root 3. Who agrees that everything I've done here is correct so far?
Yeah.
You guys, I tricked you all.
Oh, my.
Okay, where's the mistake at? What is that? The x coordinate here. We are in Q2, right?
Oh.
X is negative.
No way. That's hard. That's hard. So hard. Nope. That E.
Now we're good.
We're elbows.
Ava.
Oh, stretch.
Oh, okay. Stretch, get your stretch on.
Alright, that was a crazy move right there.
Little small detail. Is that important?
Yes.
Oh, yes. Big time important.
Oh, yeah.
Because the x coordinate, your point, is in quadrant 2. To get into quadrant 2, you have to move your x to the left. That x coordinate must be negative. Even though we obtain that x coordinate by looking at the side length of a right triangle, we know that x coordinate is not the length of the triangle. It's that distance of the right triangle away from the origin, but we have to still consider we're going left or right or up or down.
Wow.
So you have to be careful there about the quadrant in which you're working in.
That was a good one. What the heck?
Okay. Is everybody on board so far?
Yes, sir.
We'll make one little alteration now to make our lives a little bit more standard. Because what you've seen is we can pick that P to be anywhere, right? And we'll still all get the same answers, but we want to standardize this process so whenever anybody does this, we're all going to pick the same P for the same angle. Well, we don't want to use 0, 0 because that's not technically on the terminal side. It's at the vertex. It's not on that arm of the triangle. So the way we're going to pick it is so that the distance from P to the origin is always the same. What do you suppose we're going to pick that distance to be? 1. So, if we do this, if we've now chosen P to always be 1 unit from the origin, what have we described? If I take all possible P's from all possible angles, what shape are we going to end up with? A circle, right? So we're like 1 unit away, 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 right? You're going to end up with, well, I'm trying to draw a circle. I'm handicapped by my own artistic abilities. It looks like an egg, I know. What kind of circle is this? This is called a unit circle. Yeah.
No.
Why do we call it a unit circle?
So easy.
Because the radius is 1. So, if we've done this, recall that our definitions for sine was y over r, right? But now we're on a unit circle. R is 1, so this just becomes y. Cosine theta was x over r, but we're on a unit circle, so that just becomes x. Tangent theta was y over x, but nothing changes there because there's no r involved. Cosecant theta was r over y, but again, we're on the unit circle, so that just becomes 1 over y. Secant theta was r over x, so that becomes 1 over x. And cotangent theta just was x over y. Nothing changes there because there's no r involved. So what do you notice here about sine and cosine? The sine is the y-coordinate of your point. Cosine is the x-coordinate of your point. So the points on this unit circle all will be of the form cosine theta comma sine theta. So this is our third now extension. So now what we have is sine, cosine, etc. are defined from points on a unit circle. So instead of even a terminal, like even an angle, like a standard position angle, we don't even need that anymore. What we just have now are points on a unit circle. Yes. Does that look good? Sure. Rita.
So is P just like any point on the circle?
So P can now be any point on the unit circle. So there will be only one P that we're going to use for like cosine of 150 degrees, and it's where that 150 degree angle intersects our unit circle. That's our point P. So before, what we had, when we had like our, stop talking please, our 150 degree angle, right? We could have picked P to be here, or here, or here, or here, or here, right? Any of those were valid choices for P. What we've decided now is that we're only going to pick this P, the one that is 1 unit away from the origin, or that it lies on this unit circle.
I don't know like standard position.
That's when we draw the initial side on the positive x-axis, and then the terminal side rotates that many degrees. That's all we're saying from standard position. That setup is a standard position angle. All right. What we're going to do when we pick up next time, listen please, listen please. Shh. We're going to use the 30, 60, 90 and 45, 45, 90 triangles to create the values or to build some points on the unit circle. So those are going to build out some common points on our unit circle that we'll use over and over and over again. We'll do that together in class next time. After today, you guys would be able to do up through 50. Remember, none of this is due until
I don't care. So next weekend.
next weekend.
And I'm not gonna do it till the night before next weekend.